Greetings and welcome back. Uh, we have already seen the introduction as well as the motivation for studying semiconductor device processing and IC fabrication and various aspects of it. What's the current status in the industry? Some broad overview we already had. So now we move to process integration. I'm trying to show how do you put together the various processes so that you can actually build ICs. But before we jump into that, I want to give some background information. It is very likely many of you already know all this. First part will be about doping and compensation, because it will keep coming, and how do you make N region into a P region and so on. And the second part is the lithography step. Once you know the basics of lithography, one need not discuss it during the process integration. One can just say that lithography step is done and the regions are defined. So I'll give some basic background information in this particular lecture. So the disclaimer: first part, I would like to talk about doping semiconductors and compensation. Please note that most of the processing in VLSI is done with the help of silicon substrates. That's a mainstay. And as already mentioned, typically we use MOSFETs. So here I'll talk about doping of semiconductors, particularly in the context of silicon. So as we have seen, this is the NMOSFET schematic. We already saw some aspects of these figures. This is the three-dimensional image of a MOSFET, which is cut, and you are able to see the source and the drain and the substrate. And here I have drawn the another schematic of what is happening in terms of the cross section. So remember that it's a three-dimensional image, but we are seeing the cross section here. And as far as the processing is concerned, we look at it from the top of the wafer. So a three-dimensional structure is built on the plane of the substrate, and then we keep building various parts of the device. So as we discussed, it's a planar process. Planar process means there are devices and circuits that are built on the plane of the silicon substrate. And then the key part to note here is, and which is the emphasis of this particular background information I'm going to provide, you'll find that various parts of the wafer and various regions on the wafer are doped differently. So that being the case, what is happening? How do you do that? And there is a standard understanding which will help in knowing what is to be done. So typically you will find that you will have a P well. That is because NMOSFETs became very popular initially, and that tradition has stuck. Although we use CMOS, where both NMOSFET and PMOSFETs are available, but typically it's a lightly doped P substrate, in which we have a P well when we want to build a NMOSFET, and similarly for building a PMOSFET we will have an N well. That we will see at the right time. The N plus will be source and drain, and on the other hand there is a lightly doped region which we call it LDD, lightly doped drain, that is N minus, so lightly doped N. So that means that various parts of the cross section you find different doping, and this is not just the cross section, also across the wafers the various parts will be doped differently. So what is happening here? So for that we need to go back and just take a bird's eye view of what the silicon substrate is all about. The silicon substrate is a silicon crystal which has a tetrahedral structure, and here of course it is shown to grow on the bottom side, but this pervades in all the three dimensions. So each silicon atom is connected to 4 other silicon atoms, which in turn is connected to 4 other silicon atoms, and so on. So silicon has 4 electrons. So since it's connected to 4 silicon atoms, the outermost orbit electron of the silicon is shared with the other silicon atom. So they formed what is called a sp3 hybridized system. So there will be 4 bonds that is available per silicon atom. Now note that silicon is sp3. There are other material systems like graphene and all, which is sp2, which is on the plane. We don't usually encounter that, we won't encounter that at least during this course, but there are certain materials where sp2 also you might have to consider, but this sp3 is what we are looking at here. Now this arrangement in silicon gives rise to something very interesting. Silicon being tetravalent, In its place, if you put a pentavalent atom, of course, it's not automatic. All atoms may not always work the way you want because of the temperatures at which you can put it and size of the atom and so on. But in the case of silicon, if you are able to put phosphorus, arsenic or antimony, they are pentavalent and they can stay in the place where silicon atom is present in the matrix. That means there is an extra electron that is available in these. It turns out that extra electron, the fifth electron in the outermost orbit that is there, when it is in the matrix, it is prone to jumping to other atomic locations. Although originally there is no orbital for that, no electron available in the silicon, but the fact that it's lightly held by the phosphorus, it easily goes and jumps and goes to the appropriate place with a little thermal energy to the appropriate place in the silicon band structure. So this gives rise to N-type doping. And similarly, if you can replace the silicon with a trivalent atom, boron, indium and so on, they have one electron less. So it's like an empty space that is present. So if you look at this schematic that I have shown, boron with an empty space, so it is as though another electron from a neighboring silicon atom can easily jump into that location. This is one way to visualize what is happening. Typically people use a band diagram structure to understand this. So let us also try that. So this is the metric approach. So you have silicon, silicon, silicon everywhere. Once in a while you will find a boron and once in a while you could find a phosphorus. If there is a boron, this had one electron deficiency. But it turns out from some neighboring location, this silicon location, this electron has jumped to this. That means this has 4 electrons around that particular atom or ion or that nucleus of boron, but in the outermost shell. But in silicon, you will find that there were supposed to be 4 electrons, but this electron has gone to boron. So that means there is an empty space. It appears as though there is a hole there, and that's a concept of the hole which I am sure all of you are familiar. Now, similar thing happens with phosphorus. Phosphorus had an extra electron that ends up jumping to one neighboring silicon. In this case, I have shown it schematically jumping to this particular silicon atom. So that electron is loosely held and it can actually move around. So this hole that is present is absence of electron. It turns out to be like a positive particle. So if a field is applied, it can move around. And similarly, this electron, this can actually move around when a field is applied. So although there are all sorts of electrons present which are bound, but when we say electron in a silicon substrate, it's actually this loosely held electron coming from a dopant or sometimes thermally generated electrons. And similarly, holes are what is caused by the acceptor atom. So borons are usually called, boron type purities are called acceptors because they accept electron, and phosphorus type dopants are called donor dopants because they donate an electron. Please note, in the semiconductor matrix that we have, in the semiconductor matrix, you have huge number of silicon atoms, and these dopants actually occur once in a while. It could be parts per 1000 or parts per 100 nowadays for heavily doped substrate. But so there are 100 silicon atoms, you may find one phosphorus. That's the extreme case, but typically it's parts per million. There can be million silicon atom or even a billion silicon atom, and there can be one particular phosphorus or one particular boron which is coming there. So that's why it's called a dopant. It's actually doping it with a small amount, and that causes it to be N-type or P-type. So the missing electron in boron manifests itself as a hole. So boron is an acceptor, is an acceptor dopant. The hole which is there from phosphorus, so this hole that is created because of boron can move around the whole lattice. Similarly, the extra electron in phosphorus manifests itself as electron, and the electron can move around the whole lattice also. So as I mentioned, the dopants are very rare in the silicon atom, silicon matrix. So this is the physical view, but to really understand what is happening, often the energy diagram is what is needed. So let us understand that, and that with the help of that we can also understand what is this compensation, at least the broad overviews. So typically you must have all encountered this. This is the how you express the band diagram. Of course, it hides a lot of information, but only the key information that we want comes here. So the top line that you see is the bottom of the conduction band. These are all typically empty, and the line here you see is the valence band top part, and the vertical axis of course is the energy here. And these the valence band is typically fully occupied by electrons, and the Fermi level appears somewhere in the middle if it is pristine. Pristine means there are no dopants, nothing, it's pure silicon crystal. So that ends up becoming intrinsic, which essentially means the number of electrons is equal to number of holes, and these are actually just created because of some thermal disturbance that will be there at that particular temperature. Typically at room temperature it is around 1.45 10 to the power 10 per centimeter cube. So this is more than a billion less than the number of silicon atoms that are present. 10 to the power 22, 23 is what you should get in a typical semiconductor. So intrinsic thing for silicon is far lower than the number of atoms of silicon that are present. So that's why it appears almost like an insulator. But supposing I ended up putting some dopants, and here this dopant that we put, it's a concentration of Nd per centimeter cubed, that ends up creating an energy level almost hugging the conduction band edge, Ec. So Ed is the level created because of the dopants. Now what ends up happening is, this is where the extra electrons of the phosphorus, arsenic or antimony, depending on that the energy levels will be defined, but it is so close that it's as though these electrons are close to the conduction band, so they can easily jump into that. So these can end up giving a large number of electrons even at room temperature. Okay. So intrinsic electrons had to jump from here to here, and that's why you got this small amount of stray electrons and holes that were present, right, which were the intrinsic carrier concentration. But when you dope it with Nd, you find lots of electrons coming here. So in this particular case, this ends up becoming what they call is as an N-type, because there are huge number of electrons that are created because of the dopants that are present. Notice that the number of dopants that you Nd is usually much larger than Ni. To give an order of magnitude, Ni we saw is of the order of 10 to the power 10 per centimeter cubed. Nd in a starting wafer could be 10 to the power 3 to 10 to the power 16, depending on how much money you are willing to pay. Typically find that it's low, but still it is much larger than Ni. And once you start processing, this Nd can be tuned to go all the way up to 10 to the power 16, 17, 18, 19. Sometimes people even dope it up to 10 to the power 20 and so on. So in order to get lots of carriers. So notice that Nd typically is much larger than Ni, and in this N-type material, N would be nearly equal to Nd. This approximation is pretty decent, and the whole concentration, because it's in thermal equilibrium, it will be Ni square divided by Nd. So essentially Ni square by N, which is Nd here. So this is the doping with donors. Similarly, you could also dope it with acceptors, boron, indium and so on. In acceptor, you get an acceptor level which is almost close to the valence band, and that ends up giving you opportunity for electrons that are present in the valence band to jump into the acceptor level. So when it jumps into the acceptor level, holes are created here. The concentration of holes becomes nearly equal to the concentration of the acceptors that we have put, that is Na. So this is called p-type. So usually Na is again much larger, the dopant that you put is much larger than Ni, but of course much less than the concentration of silicon atoms, as I mentioned. So P would be equal to Na, and N will be equal to Ni square by Na. So this is how, from a pristine silicon without any dopants, assuming that you are able to somehow get that, you can put some dopants and make it N-type, or you can make it P-type. But then there is something else that is equally important, and that's what we are going to see now. So supposing silicon contains both Nd and Na, then what happens? Can it be n-type or can it be p-type? And it turns out that it can be either n-type or p-type. So, let us see what it is. So, if you see here, n-type silicon will be, if it will be n-type silicon if Nd is greater than Na. So, the concentration of dopants that causes Ed level, if it is larger than the concentration of dopants that causes this Ea level, then it becomes n-type. While it just has to be greater than this for it to be n-type, it turns out that usually Nd is much larger than Na for the reasons of processing. You cannot control it so precisely. So, usually to make sure your process is reliable, you dope much larger than what the background doping is. So, you end up getting Nd to be much larger than Na. So, in this particular case, you will find that N will end up becoming Nd minus Na, and of course, if it is much larger, you can even ignore Na. Okay? But if you want to be very precise, Nd minus Na, and the P ends up becoming Ni square by Nd minus Na. So, in this case, since Nd was greater than Na, it ended up becoming n-type. On the other hand, this could also be p-type if Na was greater than Nd. So, it depends on the dopants you have put. If the dopants which are causing this Ea level is larger than the dopants that are causing this Ed level, it ends up becoming p-type. Okay? So, and here again also for practical purposes, typically Na is much larger than Nd. So, P is equal to Na minus Nd. You can make it approximately is equal to Na also, and N equal to Ni square by Na minus Nd. Okay? Now, the fact that both are present and yet it becomes n-type or p-type, that is because of what is known as compensation. So, whatever is excess, if donors are present and you put a lot of acceptors, initially all the acceptors will go to compensate all the donors, and the remaining ones will end up creating the p-type material. Similarly, if there are lots of acceptors and you put even more donors, then the donors initially will go and compensate all the acceptors, and the remaining ones will give the n-type materials properties. So, this whole phenomena is known as compensation, and this can be leveraged in order to create p region and convert it into an n region or parts of it into n region and so on. This is what is done in the VLSI industry, and we will see that routinely as we look at processing. So, let us quickly look at one key aspect. This is a conceptual point, so I want you to imbibe it. From a practical point of view, it is a conceptual point. Assume that you have a starting substrate which is Na, which is p-type, and this is what is typically the case, because historically this is how it started, but today both are available, and usually it is so lightly doped, it does not matter whether it is p-type or n-type. But supposing it is p-type with background doping of Na, when you purchase it, it will be 10 to the power 13 to 10 to the power 16 per centimeter cube, and 10 to the power 13 to 10 to the power 16, when you say 10 to the power 13, it is very difficult to bring it to very low levels of impurity, because purifying costs money, but today we have achieved this, which is pretty remarkable. Now, you can make, once it is there, in processing typically you cannot make anything which is lightly doped than what is already available. So, you can put extra dopants and convert p-type to n-type, or p-type into more heavily doped p-type, and so on. So, extra dopants, supposing that whatever you are putting, you typically want to make it much larger than Na. You do not try to put it just equal, and you can never make it just, even lightly doped is tricky. There can be certain parts of the wafer which end up becoming more doped by what is you have put in, and some parts which are not compensated sufficiently. This is because of the practical challenge of uniformity. Uniformity typically can be of the order of 10%, if you are really careful maybe 1%. So, even if 1% is there, if 10 to the power 17 is a doping, so you can see that plus minus 1% will be going around that whenever you do the implantation. So, to exactly compensate and make sure everything is compensated is a challenge. It is a very practical situation. So, this is the reason for the practical constraint, that you can never make it lightly doped from what is heavily doped. Whatever is the doping, you can only go make it more heavily doped, but not lightly doped. When you make it more heavily doped, you just need to put more of the same atom. For example, if this p-type, Na is a background doping. If I want to make it more p-type, I put more Na, and then it becomes more p-type. And if I want to make it n-type, I have to make Na plus Nd, where Nd should be much larger than Na. So that way we compensate, and we can almost say it's equal to Nd1, that is the doping that is present there. So I have shown here for a p-type substrate, so same arguments can be made with the starting n-type substrate. So essentially what I'm trying to tell is, you can have a substrate where you can convert from p-type to n-type, but when you convert it from p-type to n-type, it has to become more n-type doping than original p-type doping. Similarly, if you want to convert n-type into p-type, you have to dope more heavily. So essentially you have to dope more heavily there. So let me quickly flash a few doping profiles. So typically you will find a diode, for example, if I am starting with the diode, p region n plus, and there is a p plus. So the diode is actually n plus p. Okay. Although in theory you can have NP, and there are cases where you can get NP in the lateral dimension and so on, but typically when you want to have a vertical device, this has to be much heavier doped than this. So it leads to n plus p, and as you might have studied in device physics, it's called a one-sided junction. Actually, it turns out that it's very convenient to analyze a one-sided junction compared to similarly doped in a practical situation. And similarly, if you notice, the p is connected to p plus, and then you put a metal contact. This is important because in order to make an ohmic contact, the metal to semiconductor, if the semiconductor is heavily doped, you can be sure it's an ohmic contact. If it is lightly doped, it may be ohmic or it may be Schottky. The reason is, it depends on the work function of the metal and the semiconductor. So if you want to forget about what the metal's work function is and what the semiconductor work function is, and you want to make it ohmic, just dope the daylights out of it at the contact region. And so P and P plus, the barrier is going to be very less. So it's almost a very small voltage drop between this, but the contact will be very good. On the other side, since it's already N plus, you don't need to do any other implantation. The metal semiconductor will be an ohmic contact, and the junction will be this. So essentially, diodes are one-sided, and this has advantage in device analysis also, it turns out, if you remember your device physics. And for contact of the P well, for any contact which you want with the outside world to the semiconductor, that region should be heavily doped, preferably of the same type to the region you want to contact. So if it's a P well, you want to have a P plus and then contact it. If it is an N and you want to contact it, you make N plus and then make a contact. So heavily doped semiconductor is ohmic contact, and doping regions are formed more heavily than the. So it works out in our favor, since our doping has to be larger in concentration than the background concentration of the existing dopant. It's actually an easier thing to do as far as this process is concerned. Of course, you cannot reverse the process. That's a challenge. If you want to reverse the process, you'll have to melt the silicon and do something, or maybe there are some other tricks, but they are very costly. And finally, same can be observed as I showed N plus P. Similarly, P plus N also you can make. Similarly, you can also make a BJT, N plus Pn or P plus Np. If you remember your BJT, the doping actually decreases as you go inside the device, or as you build it, you go for higher and higher doping regions from the collector to the base to the emitter. And similarly, in the MOSFET, you have a source drain implant, right? This is of course not a MOSFET. Here I am showing a diode, which I have shown above. But a MOSFET will have an N plus in a well, and similarly P plus in a N well. So that will end up giving you the junctions that are needed to create the source and drain, and also it's useful to make the contacts on the heavily doped source and the drain region. So quickly, the takeaways: silicon substrate can be doped to make N-type or P-type. Okay, so this is something important and wonderful. This is why semiconductors are amazing. You can tune it. This is not possible typically with insulators and conductors. You can tune it over orders of magnitude, and you can also flip it from hole transporting region to electron transporting region. That's the amazing part of it. You can compensate N-type with acceptors to make it P-type. And for this, you made accepted dopants to be larger than the dopant concentration already present, but preferably it should be much larger from the practical point of view to ensure error-free operation, error-free processing. And similarly, compensate from p-type, it's just the symmetrical thing. Donors, we can make it n-type. For this, Nd has to be greater than Na that was already present, but preferably Nd should be much larger than Na. Practically, it is not possible to make a wafer more lightly doped by compensation method. There could be other methods, but typically they are very costly. But the compensation method you cannot. But we will use this compensation method repeatedly. And remember that when you're converting some region to other region, it should be more heavily doped. Okay, now let me start with the discussion about photolithography patterning. And the reason I am taking this up separately is because it keeps repeating again and again during a process integration discussion. And so once it is known how photolithography is done, it's like a module, you know what happens, so you can understand what is being attempted. So as again coming back to the same top figures, if you have, you will find that there are various regions in the device. The device is not just a flat uniform thing, right? There are various regions. Some region is n-dope, some p-dope, somewhere oxide is formed, somewhere oxide is not formed. Sometimes isolation is formed, sometimes not formed. So what it means is there are patterns that you notice when you look at the wafer from the top. And this pattern is typically created. There are a few other techniques too, but typically it is created by lithography. And the lithography is a mainstay of processing. And also, as we saw earlier, the lithography needed to form the gate dimensions defines the technology. But besides that, we need lithography for various process steps. And that lithography is the critical IP part of the processing design, that is the circuit design. So typically, in any processing, you will have steps which are addition. So you start with the wafer as a default, you will have something, it need not always be so, but typically you will start by adding something onto the whole substrate. Whole substrate will be filled with something. After the addition, you typically do some patterning. Actually, this is not in sequence, but this you actually pattern it. After you have patterned it, regions you are wanting you can etch, and the rest of the regions will remain as they are. Alternatively, you can start by subtraction. You can etch something on the wafer, then you can pattern it and fill it accordingly. So that is one thing, but typically for lithography it is addition, lithography, and then subtraction. So let's see how lithography can be done on a substrate plane. So we start with the substrate. Okay, we start with the substrate here. So substrate might already have patterns or structures from an earlier processing. We are not looking into that. We will look at that when we do process integration. But here I am just showing some substrate just to illustrate the lithography aspects. Then we coat the wafer all through with a photoresist. Okay, full zinc substrate is coated with a photoresist. This can be done by spin coating, and typically is done by spin coating, and there could be other ways of dispensing it as well. Now the photoresist that we use, they usually categorize into two parts. One is called the positive photoresist and another called the negative photoresist. And the reason, as we will see, is quite obvious why it is called so. So let's go forward in the processing. So if you see, there's exposure to light through the mask will help you define the regions in the photoresist. So let's see how that is done. So supposing you have this, we already saw this substrate with the photoresist coated on top, and supposing you bring a mask. The mask has two regions. The black regions are where the light cannot go through. The blank region is where light can go through, as you can see. The exposure of the photoresist is through a mask, and the wavelength you use will be appropriate to the photoresist you are using. Okay, the photoresist should react to that particular wavelength. Either the polymers will end up combining together and become more rigid, or when exposure of light happens, the longer polymers break down to smaller units. So if you go by that, the mask that you want, these regions will be determined by what you want to make, what pattern you want on the substrate. And so the dark part and the opaque part and the transparent part is what defines the pattern. So let's take the two parts. As I said, there are two parts. First is for positive photoresist. Let's look at it, and then let's look at negative photoresist. In positive photoresist, we'll end up exposing. So remember that light goes through this region, central region, right? So wherever light goes through, you will find that the photoresist may become softer or easily soluble, and I have shown this with a lighter color. So in a positive photoresist, this polymer ends up breaking up wherever the light comes, right? And so it's the photoresist softens on exposure to light. Now in the negative photoresist, opposite happens. Wherever light falls, the polymers get more interlinked. So you will find that it actually becomes more hardened, less soluble. So post exposure, the photoresist hardens wherever exposure happened in the negative photoresist. So now if you go forward, on the left side we have positive photoresist where central portion was softened. So when I dip it now in a developer, the region which is softened will dissolve faster, and you will find that an opening is created. The region which is not exposed will not dissolve as much, so they will remain. On the other hand, in the negative photoresist, the part which was exposed becoming more hardened will not dissolve very much when you are developing it. On the other hand, whichever was not exposed to light, they open up. So you can get patterns based on the same mask using either positive or negative photoresist. Of course, if you are using a positive photoresist, you use appropriate mask. If you are using negative photoresist, you use appropriate mask. So the surface of the substrate is now patterned, as you can see, because of the exposure and the development. The positive photoresist, an opening is created, and in the negative photoresist, a region which is blocking is created, correct? Now, if I know pattern on top of it, I could do implantation, I could do etch, I could do exposure to some gases. So the region which is exposed will interact directly here and here. The region which is blocked here, you will find that whatever you are processing will not affect the substrate underneath. Of course, you have to make sure the photoresist is thick enough to ensure that. So this is the first order method of patterning and creating areas where processing can happen. So substrate plane is now differentiated with photolithography. This is the key aspect of photolithography. By doing lithography, the plane is differentiated into regions where you are exposed to the outside or you are blocked to the outside. And now once it is there, you can do processing on that. So let me come to the takeaways. So takeaways on lithography patterning. First of all, one can create exposed and blocked region with photoresist. So the plane region is differentiated with what is exposed and what is not by using a photoresist and playing with it appropriately. You expose the photoresist through a patterned mask. So whatever feature you want on the wafer, you better have the mask prepared accordingly. The photoresist softens wherever the light falls, and the exposed part dissolves away on developing photoresist. Negative photoresist hardens with where light falls, and of course non-exposed parts dissolve away in this case. Okay, the part that is exposed remains where it is. So after this, you do the whatever processing you have. What you do in the end is you remove all the photoresist, whether exposed or not. So there are various ways of doing it. You can use stronger solvents, or you can even ash it. You can put it in an oxygen plasma, and it just ends up burning up the polymer that you have, organic material you have. And typically organic material just burn off whenever you are exposing it to oxygen plasma. So this is the way you can do lithography. So now we are armed with this. Let's go forward and look at process integration.